Okay, so this is part two of my overview of OSPF characteristics. We were talking about things like the basic components, the basic process. Now we're going to talk about the single versus multi-area OSPF, OSPF message encapsulation, hello intervals, the things that you would find in the link state advertisements, the LSAs, etc. Um, the simplest possible implementation of OSPF is single area OSPF. All your routers are contained in a single area. That is area 0, which we call the backbone area. This is good for a small network with a limited number of routers, say a campus area network, particularly a simple one, say a mere handful of buildings. Now, if you have a large campus area network with a large number of buildings, large number of hosts with a more complicated subnet scheme, you may actually have to implement what we would call multi-area OSPF, which is this over here, even on that campus area network. Now, if you're talking about not just a local or campus area network, but a true wide area, metropolitan area network, a MAN, or even a wide area network, a WAN, belonging all to the same organization, functioning as an autonomous unit, shall we say, you're definitely going to need OSPF, because the core of that network, the backbone of that network, might be your area 0, whereas the rest of your network might be, say you've got a campus at one location and it's area 1, and a campus at another location and it's area 51. Also, there are little green men there. Anyway, so multi-area OSPF is designed to be built hierarchically and really only works well that way. All the other areas connect through area 0. Area 0 is still the backbone, and now it functions as one. It is the conduit, shall we say, between area 1 and area 51 and area 2 and area 10 and so on and so forth. And so it is, I mean, if you can think, you can sort of think of the areas distributed around area 0 like a hub and spoke topology. Imagine a central location with many locations scattered around it, which is one of the WAN topologies you'll discuss in connecting networks. The routers that are connecting off some other area to area 0 are what we call area border routers. So now we have with multi-area OSPF, we'll start introducing the concept of router roles. With everything in the backbone, everything is an internal router, except maybe if you've got one of those backbone routers, which is also connected to a network you don't control. That would be an ASBR, an autonomous system border router. Multi-area OSPF is good for larger networks. Now, one of the virtues of multi-area OSPF, now with single area OSPF, every router has to know about every other router, and every router will react to a topology change by recomputing its own SPF tree. If you've got a small number of routers and a small number of subnets, that's not a big deal. If you have a very large number of routers and a very large number of subnets, and they all have to recompute every time any of them goes sideways, that's a problem. One of the virtues of multi-area OSPF is that multi-area OSPF, each area has its own link state database. So there's convergence in area 1 and convergence in area 0 and convergence in area 51. But if something goes sideways in area 1, area 51 doesn't have to reconverge. Now, area 1 may advertise new information through area 0 to area 51 about the networks in area 1 that are no longer available, but it's not obligated to do so. Well, it is, you want it to do so. But area 51 is not going to spend all its time recomputing itself because interfaces are going up and down or flapping in area 1. That's one of the good things. So now let's talk about OSPF messages. Now, OSPF Um, from the perspective of encapsulation, and I'm going to play the bounce myself around game. From the perspective of encapsulation, you can sort of think of OSPF as a upper layer protocol because it tags on a header after the layer 4 header. Um, the header the IP header will contain either a multicast address. Now this is one of those other things that you should tattoo on your brain. We talked a little bit about multicast addressing when we talked about ERGRP. If you see 224005 or 224006, that's OSPF. By the same token, when we talk about V3, if you see FE FF02 colon 5 or FF02 colon 6, again, that's OSPF multicast. Your packet header will indicate the type of the packet, your router ID, and the area ID. And the packet type will also contain some information about the packet type. It'll indicate whether it's a hello packet, a DBD, a database description packet, a link state request, a link state update, or a link to state acknowledgement. Now, the protocol field in the IP packet indicates if you see a protocol field value of 89. Now, remember, in a layer 3 header, your protocol field kind of says what's going on at layer 4 or 5 or 6 or 7. So it indicates, hey, it gives some clue as to the payload, shall we say. Let's talk about message encapsulation and those packet types. So, OSPF v3 has similar packet types. We've got type 1, which is a hello packet. You use these to discover your neighbors, build adjacencies. It is also used empty as kind of an acknowledgement packet. Your database description basically tells the adjacent router, this is what information I have. Notice, please, that the database description is just kind of, hey, I know about this. It doesn't contain full details about the things it knows about. The link state request, so when an adjacent router receives a hello packet, it establishes a neighbor relationship, it sends out a database description, a DBD. The neighboring router looks at that DBD, and says, hey, this guy knows things I want to know. Tell me more. That tell me more, that request for information is your link state request. The router which advertised the DBD, the information it has, sends a link state update. So the link state request says, okay, tell me more about your path to 192.168.100.32 slash 27, sorry. And then, so the router which receives that link state request will say, okay, yeah, here's what I know about, here's my cost to 192.168.1.32 slash 27. And when the router receives that information, it will send back a link state acknowledgement. So let's talk a little bit more about the hello packets. Okay, now, you don't, hello packets, as I said, are used to discover neighbor adjacencies, advertise information about the router. They can also be used for things like DR and BDR elections on your multi-access networks, specifically Ethernet and frame relay. So if you're using OSPF over a serial line, that DR-BDR thing is irrelevant. But if you're using OSPF in a multi-access network, either a broadcast or a non-broadcast multi-access, frame relay, Ethernet, you absolutely have to elect a designated router and a backup designated router, and all the other ones become DR others. We'll discuss that in more detail, I believe, in chapter 10. So we get your hello intervals. Now, if these hello intervals don't match, router adjacencies don't form. So it's important to have them so they can keep in sync with each other, but if they also advertise them. And if there is a BR or DR, those router IDs are included. So this is how how a lot of the information you see in your neighbor table comes from. And a lot of the information you would see even in IP protocols and show OSPF database, all that stuff is coming out of this information. You also see fields for authentication type and authentication values, things like that. So this is essentially your upper layer header, your upper layer data. Let's talk about hello intervals right quick. So, the hello packet intervals are a key component of neighbor adjacency. Another way of saying that is if your neighbor, your hello and dead intervals don't match, the neighbor adjacency either won't form or if it has formed, will fall apart. So if you're troubleshooting OSPF and you think you should have neighbor adjacency because everything else is working, but you still don't have neighbors where you expect to have neighbors, do show run interface and look at those hello and dead intervals. Every 10 seconds on your multi-access networks, it will send out a hello packet. And about every 40 seconds, it will give up. What these hello packets do, and we saw a little of this in one of my OSPF demo videos as I was refreshing show IP OSPF neighbor and watching it tick down after I had broken an adjacency. Every hello packet refreshes, refreshes, yes, that's exactly the word I want to use. Every hello packet refreshes that countdown, so it never reaches the dead timer. But if there's too many missing hello packets, and it will count down to that dead timer and stop. Dead intervals are always 4 times the hello interval. So if you change one, make sure you change the other. If you change one, make sure you change all of them. Now, one thing to note, these things are set at the interface level, not in router config, in interface config. So if you have one of your interfaces that is fast Ethernet or gigabit or whatnot, it can run using your standard, using your 10 and 40 timers. Whereas if you had, say, a non-broadcast network, it's going to go every 30 seconds and wait 2 minutes before it really times out. So when a dead interval expires, because the router hasn't received not just one, but has missed 4 successive hello packets, OSPF is going to take that neighbor out of its neighbor table, out of the link state database. It is going to recompute. It is going to flood that information downstream to all its neighbors that it knows about. That's how it detects topology changes. Well, one of the ways it detects topology changes. It may also detect topology changes on the basis of things like its access layer networks that go down. It'll also let other networks know, hey, things have changed. But it's definitely going to, every failed neighbor relationship will cause a topology change throughout the whole area. That's hello packets. The next thing I'll talk about is link state updates, how they work. So be right back.